Hello everyone, welcome back to Spectrum classes. In this video, we are going to discuss phase of a particle executing simple harmonic motion. I will take these examples at the end of this video. Before that, we are going to discuss the geometrical interpretation of the phase so that you have better understanding related to the phase and its position. So for that purpose, we are using this equation y is equal to a sin omega t. This is for the particle executing simple harmonic motion. And if it is sometime deviated from its equilibrium position, then we introduce phi naught. So this is called initial phase, right? And here some of the students get confused why you are using this, why you are not using this equation. So this is used for the waves and we are going to discuss it in the next video. We are not going to discuss it here in this video, right? So let's start with the video. And what is called phase. So this phase represents the position and the direction of the motion at time t. So first I will give you the definition of the phase. So what is called phase? Phase of a vibrating particle at any instant is a physical quantity which completely expresses the position and direction of the motion of the particle at that instant with respect to its mean position. So that is important. Now this is represented by this equation y is equal to a sin omega t plus phi naught, and here this omega can be written as, this is the angular frequency, so this is equal to 2 pi nu, where nu is the linear frequency, and this will be represented by 1 upon t. So we can simply write down 2 pi upon t. So on replacing this omega, 2 pi upon t into t plus phi naught. So this equation can be represented by this manner also. Now the quantity 2 pi t upon capital T plus phi naught is called the phase of the oscillation at time t. It is denoted by phi, and here I have written phi naught. So phi is equal to this much, right? And initial phase or epoch, it is the phase of a vibrating particle corresponding to the time t is equal to 0. If I put t is equal to 0, then phi is equal to phi naught. And this phi naught is known as its initial phase, and this is also known as epoch. Its unit is in radians. The vibrating phase of the particle changing continuously with the time, but the epoch remains constant at all the time. So here you might get confused. So I will explain this line with the example in the next slide. So here we are going to discuss the geometrical interpretation of simple harmonic motion. So I have drawn this circle, and at this circle this O is the mean position, and here P naught is the particle which is moving with the angular velocity omega on the periphery of this circle, right? So let's do it. And this is the omega, which is angular velocity of this particle, and after time t this particle will be at some point here, right? Now I will draw the lines from this point pt to the origin O. So if you don't understand from where this path comes from, so I have discussed it in detail in my previous video. This is comes from when this P naught is moving about this periphery of the circle, then the particle which is sitting on this mean position O, that will vibrate in a simple harmonic motion up and down. I will show you in the next slide. So this comes from there only, so I am not elaborating it much here. So I have drawn a line from this point after time t. So here what we see, here we see this particle P naught is moving with the velocity omega, and after time t there is a displacement. So this displacement is represented by this theta. I have also shown over here. So this is the radius of the circle, and this is the angle theta, and this theta is equal to omega t. I have also written that. So theta is equal to omega t. Clear? So this is from the circular motion we get. And here I have drawn another lines which is shown by this light blue and green. So these are the perpendicular from point PT on the x-axis and on the y-axis. Now by using the trigonometric functions we can calculate the x-axis and this y-axis. Y is from this to this, right? So here what you see, this is the angle theta, because two parallel lines, green and blue, are the parallel, and one, this PTO line, red line, cuts down these two. These two are alternate angles, right? And from here we can calculate this ON and OQ values. I have written this. ON is equal to Y and this is equal to A sine theta by trigonometrically, right? So if you are a biology student, then I will make a separate video on this. But here, just because of the length of the video, I am just going to avoid all such things. OQ is equal to X is equal to A cos theta. So here, these two are the projections of this point PT, of this point P after time t. And similarly, the theta angle will change if my PT will be going on the periphery of the circle. So here theta angle will be omega t, as I have shown you earlier. Now here omega represent angular frequency of the particle n, and for particle p it is angular velocity, and omega t is known as the phase of the particle n moving in simple harmonic motion. So this is very important actually, and you need to know this, right? If we started at point P naught, we get this kind of waveform. But it can also be possible that when I started measuring my time t is equal to 0, the particle P can be here at this position, or it can be here at this position. It is not necessary that it always be present on the equilibrium position, right? So for that purpose we are going to solve this equation in this slide. So suppose when I started measuring my time t is equal to 0, the particle is somewhere here. So I have drawn the lines here. So first I join the line O to P naught, and second line I have joined from, this is my angle phi, because initially it is at this point P naught. So this is my initial angle. Now this particle P naught will start with the velocity omega, and for time t it moves and it reaches to point PT. And once it is moving from P naught to PT, then it makes an angle omega t at this. Here I am just going to show you. This is my omega t. So if you have any confusion, then you can write me in the comment section. Here, so if the important point is that we are going to measure it thoroughly. So from 0 to nt we need to measure. We cannot measure from n naught to nt. This is important point because a student made mistake over here. So our total angle is theta, this, and this theta will be equal to this. Here I am just going to draw this in dark. So this is our theta. So what is our theta in this case? So our theta is equal to omega, here I have written this theta is equal to omega t plus phi. You can see here geometrically. So what will be our ON? ON will be equal to A sine theta. OQ is equal to A cos theta trigonometrically, and theta is omega t plus phi. So on putting the values of theta is equal to omega t plus phi, we will get this kind of equations. So here it is, this theta is equal to omega t plus phi is the phase at time t, and at time t is equal to 0 we are having epoch, right? So this theta is equal to phi or phi naught, we can write down. So this is epoch, and this will remain same throughout the motion of the particle. So how we are going to understand this? We are going to understand this if we started with this phase difference, this from here to here, then this phase difference will remain same throughout this motion. So here this will remain same. This is also defined by the path difference and time difference that we are going to discuss in the waveforms, right? So this is important that at every time if we put t is equal to different, then this phase will change, but epoch remains same at time t is equal to 0. Now the second case we are going to consider. Here in this case my particle is here at this point P, which is below the x point or mean position. That was ahead from the mean position, now it is behind the mean position. So it can be represented by this blue line. If we started with this, then you can see I have drawn lines OP0 and OPT. My point P0 starts moving with time and it reaches to pt. So it is moving with velocity omega, and in time t it reaches to point pt. So it will make an angle omega t from here to here. Clear? So this is our omega t. So I have drawn here, this is our omega t and this is our phi. This is called initial phase, where it is from the origin. And as I told you earlier, we are not going to consider here N0 to NT. We will always consider only from the mean position. So mean position to NT we are going to measure. So if we are measuring from O to NT, then this will be the theta. And this will be the theta. So here I have drawn, this is theta. And this what this theta is here in this case. So theta will be equal to omega t minus phi. You understand my point? So this is my phi angle, which is this P0 makes with this mean position. And this P0 moves with omega t in time t, and this will makes an angle omega t. So the theta angle is this one. This is my theta angle. So this theta angle is what? Omega t minus phi. Then this will gives me theta. So theta will be this much. If you are a student of mathematics, then you can easily understand this. Now I am putting the values of theta in these two equations and I will get this kind. So here this will be epoch if we put time t is equal to 0 here in this equation. But this will be the phase if we put t is equal to something else, right? So this will be the phase t at time t, and if we put time t is equal to 0, then we will get the epoch. So here you will get the same phase difference throughout the path of this wave motion. So here omega is angular frequency for the particle n, and omega t is the phase, and this is epoch if we put time t is equal to 0. And here is the relationship, and in this relationship this theta is equal to omega t plus minus phi. So this is plus minus phi, and I have written epoch at time t is equal to 0. Just because of this plus minus phi, this relation is valid when time is noted from the instant the vibrating particle is in simple harmonic motion passing from the extreme position. Means it is passing from OX to either it is above the OX or whether it is lagging behind the OX. Then we are going to add this plus minus phi. If it is above this x, then this is plus, and if it is lagging behind this x, then it is minus. I will explain this plus minus concept in detail in the next slide. So here I am just going to show you these